All right, so it's 5 o'clock. So we have about 80 people in attendance at the moment. So welcome everybody, and welcome Jeff. Jeff Rouder is a professor of mathematical psychology at UC Irvine. He has done phenomenal work in psychology and from my perspective, done phenomenal work on the applications of Bayesian statistics, for example, in research in psychology. And in recent years, he's been doing a lot of really cool stuff on individual differences. He gave a talk at AmLab on modeling on individual differences. And I would strongly encourage you guys to go and look at that talk. If you haven't seen it, it's at amlab2020.org. It's linked over there so you can watch the talk. And so his work on individual differences has been very interesting. And of course, he does cognitive modeling too. So today he's going to tell us about robust cognitive modeling, right?
Thank you very much. Thank you for the kind introduction. I'm going to share my screen here, and hopefully, whoops, this is clear to everybody and it's big and everything's okay?
Yes.
All right, so I'm going to begin. Thank you very much. It's a pleasure to teach here. And I've titled my lecture, Robust Cognitive Models. Now, in 2018, I went to this kind of grant-funded powwow on robust models. And I didn't know what it was about, but I was able to get an all-expense paid vacation in Florida, and we ate some good food, drank some good liquor, and talked about models for 3 days on the National Science Foundation's dime, and had a great time. And then a bunch of us wrote a few papers about what we talked about while we were having a good time. And then other people wrote back and said, you're wrong, you're right, maybe you missed this. And so there was this whole exchange about what does robustness mean for models in cognitive science. And all right, fine. I was like middle author. I said a few things. I had a good time. And then people started to ask me to teach courses on this controversy and what does it mean. So SMIP is the German group on the other side of the country in Baden-Württemberg, run by Edgar Erdfelder and colleagues. And they asked me to teach a 10-hour course on robust cognitive models. And I said, my God, what am I going to teach? But it turns out I had a lot of fun, and I thought about it, and I learned a lot. So I decided to just present the first little bit of that course to you so you get an idea of what do I mean by robust models in cognitive science. So today I just want to talk a little bit about the philosophy behind modeling and the role of model specification. And I want to link in this idea of what makes a model robust. And I'll define it and the like. But before I do so, I just want to give a problem to motivate it. So I'd like to talk about recognition memory, your ability to remember things that happen in your life episodically, where you park the car when you were out last or what have you. And there's a debate whether this is based on a single process, a strength-based process, or maybe recognition memory involves contributions from several separate memory systems. So this will be kind of our motivating problem. How could we study whether recognition memory is strength-based or involves several systems? So let me just describe a typical experiment before we go any further, before we model. So I'm hoping everybody here is familiar with the signal detection experiment, which is a classic paradigm in psychology in many domains, and I'll just describe it in the memory domain. So at study, I present a bunch of items for you to study. Maybe I present 150, maybe I present them for 2 seconds each, right? But there's just a list of items that you got to remember for a later test. And then at test, I give you some of those old items and I give you some new items, right? So if you had 150 at study, maybe you have 300 at test, half old, half new. And then for each one, you make a judgment. I'm sure that's an old one. I'm sure that's a new one. Maybe it's old, maybe it's new, or I don't know. So you have these 5 categories, which I've ranked from sure old all the way to sure new. All right. This is a typical experiment in this domain. So the data might look something like this. And what I got to do is minimize this so I can see it. There we go. I hope that doesn't change the recording, but hopefully it's not on my screen that's being recorded. Um, so here are the old items I present. And of these, I think I have 100 in each. Most of them, well, not most, but a plurality of them were sure old. That makes sense. They were old items, right? But some were maybe old, some were unsure, a few were surely new. And these are the new items. And the new items are a little more distributed because they're new and people aren't as sure. And this is kind of typical of data in this domain. How can we tell if there's one process or two processes from such data? Seems like a far cry. Excuse me. Okay, the signal detection model that you're used to is based on a unidimensional strength, one process, and the idea is that for each item at test, there's a latent strength measure, excuse me, and you divide the latent strength into regions. So if it's very negative, you're sure it's new. If it's very positive, you're sure it's old. Over here is maybe new, I don't know, maybe old, and so forth. So you just divide up this latent unidimensional space with criteria to make responses. For new items, we assume the strength is normally distributed, and we're just going to center it at 0 with variance 1 to center the space. And then when you study an item, it has the distribution shifts over towards increased strength, and these are the old items. And then these distributions define area under the curve, which become the response probabilities for each of these. And this is the standard strength-based signal detection model. So to visualize the data, we do the following. Here are the old items and the new items. This was the original data I showed you. And now I've converted them to percentages or proportions. All right. And what I'm going to do is I'm going to start on this end, and I'm going to say how many responses are more sure. Well, none are more sure than sure old. The ones that 44% are more sure than maybe old, 71% are more sure than unsure, and all the way up there. All right. And so this is the hit rates, and these are the false alarm rates as by the different categories. And what we do is we plot these hit rates as a function of these false alarm rates, and we visualize our data thusly. And this is an ROC curve. Now, my hope at this point, because I only have 30 minutes, is that everybody has kind of seen this from their previous study in psychology, an ROC curve. All right. And then, as with any data and any model, we can start talking about what's the same visualization of the model. So what I've done here is I have false alarm rates down here, I have hit rates up here, and I've just drawn this model assuming that each line has all the criteria just moving across for one set of however good people are. This is not so good, better, and so forth. And so this model, as we increase the distance, the effective study, you can see these fields of lines. And this is how we can visualize the model, what the model says. And then we could put them together. All right. And so this is the data and the model. And one of the things you see is that there's actually a misfit. Early on seems to correspond to higher values in this ROC space than the model predicts. Later on is lower values. So they start kind of up on the green line and end on the red line. And what that shows is there's a little bit of asymmetry here, where there's better performance for lower. I've hit some false alarms mislabeled here. It should be false alarm on the bottom, hit on the side. But for lower false alarms, they have correspondingly higher hit rates than we would have expected. Okay, and this misfit has driven people nuts and has become known as kind of a signature of the process per se, this asymmetry. And the current way of dealing with it, which I'm going to critique heavily, is to assume that when you study an item, not only do you increase the overall center of the distribution of strengths, but you increase the variability too. And so this becomes known as the unequal variance signal detection model, where the previous model, which I'm going to go back to, is known as the equal variance signal detection model. There's the equal, there's the unequal counterpoint. All right. And one of the things that people love about the unequal variance signal detection model is it does a better job of capturing this asymmetry where you have higher hit rates at lower false alarm rates than you would have expected given the equal variance model. You see this bows a bit up here and flattens there. That's what the data tend to do. And so people are pretty happy with this model because it has a good fit. But is this a robust model? And it brings us to our first point, which is, what do we mean by robust? Do we mean the model is true? Is it accurate? Is it useful? Is it insightful? Does it tell us something about what we want to know? Is it falsifiable? Right? All these things come up in talking about models. What's robust mean? I'm going to hold that thought. All right. Let me tell you how I see modeling. This is kind of my philosophy of modeling. In my world, always starts with kind of theoretical, verbal idea statements about what may be in the world. We're going to call these theoretical statements. Memory is determined by a single process of strength. All right. And then in this real world in blue, these theories then get encoded into statistical models. And then in the statistical mathematical world, we can do inference, and then we come back and we make statements about the real world. And so we're always thinking about two levels, a real world level up here in blue and a modeling or statistical level down here in yellow and green. So this process of taking theoretical statements and making statistical models, is specification. This is what model specification means. How well did you instantiate your theories as models? Down here, this is analysis, right? You have statistical models, you have data. The models are designed to connect data to inference, and that process is called analysis. And then once you have inference, you can go back to the real world, and that's interpretation. Now, for me, specification and interpretation are actually pretty hard. I think that's where all the intellectual activity is. I think that's where we add value. Analysis for me is a little boring. It's almost always straightforward what to do. I'm a Bayesian. This is easy. Once I have the models, I just apply the one rule, Bayes' rule. So for me, analysis is always the same. Wittgenstein would call it boring, right? That's not where I'm adding value. If I don't know how to do it, if it's computationally hard, whatever, I might consult with people. But my job as a scientist is to really add value, to be judicious. The quality of my craft is through specification and interpretation. All right. What are theoretical statements? Well, theoretical statements, I'm going to give you some example. Here's one from working memory training transfer. Practicing one working memory task will increase performance in other related tasks. It's a statement about the world, about tasks. It has no concept of noise, right? It's an abstraction. Here's a mathematical one. It's still a theoretical statement that the change in increment you need to see a flash is proportional to the background intensity. It's called Weber's law. It's true. I might make one statement like performance, I should have an N in there, to congruent items is better than incongruent ones. A theoretical statement, all right? Maybe I have one in medicine, a certain drug is beneficial to all, but benefits women more than men. All these are example of kind of just statements, verbal statements you might make of the world. Even this mathematical one is still at the same level. You're just using math rather than words. Now, each of these statements describes constraint in the world, and that's the key. They tell you something has to hold, it's not everything goes. They describe constraint. And none of these statements may be tested with data. None of them are in that form because none of those statements has specification of sampling noise or errors in measurement. They don't relate to data. They're in a platonic space of their own. And I think that's appropriate. We need a space where we can talk in abstraction without the difficulties, the rigors, the the extra burden of discussing how it relates exactly to data. But the important thing is we have a space where we can say constraint. This is the constraint that's theoretically important to me. So then what models do is they take that constraint in the real world and we instantiate them as statistical models. And for me, the key to good models is that they predict data. So they're proxies. They capture constraint in theory. They're not the theory, right? But they are proxies, and they lead to probability statements on observables, so that you can say the probability of data in this interval or that interval is this much or that much. And that's what models do. That's their job, okay? A lot of people like to talk about whether models are true or false. So George Box said, all models are false, but some models are more useful than others. And what Box was trying to do is to make us take a stand against truth, right? But he didn't go far enough. I would rather take a stand against both truth and falseness, right? And I think Box should have said, I think he got it wrong. I think he should have said, all models are not even false. Some models are more useful than others. And what I mean by this is that you don't put Boolean truth values on models. They don't admit truth values. Models are not false. Models are not true. They're in a different realm where truth and falseness doesn't apply. In my work, I always think about truth and falseness as kind of for deities. But as mortals, we can't be so sure about anything. Let me give you an example. This is the Metro map for Washington, D.C. And if you fly into Washington, D.C., and you have to go somewhere, you'll actually land down here by Reagan Airport or DCA, and then you got to figure out where you have to go, be it NIH or NSF or somewhere, what have you. And so you got to look at this handy dandy map, right? And this map is a model of the Metro, right? But is it true? Is it false? These are strange questions to ask of a Metro map. So the map certainly captures something ordinal, something verbal, which is, or the order of the stations. This one comes after that one, comes after that one. And it also captures the intersections, the line. Those are the things in the world, the constraint it's designed to capture, and it does so well. But the map also distorts things, right? And it does so for good reason. It distorts the colors. So if you go down into the Metro, and I've done this many times, none of the tracks are blue, red, orange. I mean, they're such beautiful colors, yellow, but they're all steel gray, right? So these colors are made up, right? That's a distortion. And the distances, right? It really doesn't take this long to get here, right? These distances are distorted too. And thank God, because if they were drawn cartographically, the map would be much harder to read and be much less useful. So I'm not really talking about rejecting, falsifying, saying a model is true. I just think it's the wrong way of thinking about what models do. All right. Well, what do? They capture theoretically meaningful constraint and data. All right. So what this to me is giving rise to not an agenda of truthness or falseness, but an agenda of comparison. Instantiate a model, a theory as a model that places constraint on data, instantiate theoretically meaningful alternatives as alternative models, and these alternative models should place contrasting constraint on data, and then compare the relative evidence for the target model against the alternatives. So this is my revised view of modeling. We start with theoretical constraints. If we had one, we'd have a target model, and then we'd have to make up some good alternatives to contrast it to with alternative constraints. Maybe we have a few theories and each gives rise to models. Now, for some reason, I always have more models than theories. As soon as I get down to the data, I'm like, oh, that's interesting constraint also, right? But ahead of time, I kind of know what are the constraints in data, and I have them encoded in models. And then I go through and I compare them. That's called analysis. Again, just follow the rule. This is boring. This is really Specification is really fun. And then interpretation is kind of the opposite process of specification. What you went through for specification kind of guides you in interpretation. All right. So we have this model, the signal detection model. I motivated it earlier. It's the standard model of recognition memory. It's what folks use. And what I'd like to do is say, what are the core theoretical statements? What are the core constraints in the theory of signal detection? And I think the core commitment is that strength is unidimensional. There's only one dimension of strength. And so this is more like the order of the stations. It's the core commitment. All right. And then I could ask, is it testable or not? And then what's the role of the normal? Well, to me, this isn't a core thing. It's something I've added or we've added. I think it has no psychological content. It's kind of like the color of the tracks. It's just to make the model presentable, easy to teach. We could fit parameters and the like. And then, is it testable? It turns out it's certainly testable. But if it's testable, what are we testing, right? The real question is, can we test the core, not these ancillary parts of the model that don't have psychological content? Okay. I started out with two signal detection models, the equal variance one, the unequal variance one. And before I go on and talk about these, I'd like to bring in another element of robustness. So I guess the first element of robustness was this theory of modeling, that models are neither true nor false, they're instantiations, and we have to understand this, I think, to make progress. And so one thing I like about robustness, or thinking about robustness, are boundary conditions. You get this from physics. Theories don't really work well unless they work well at the boundaries too, right? There are certain boundary cases where predictions and the nature of the models become most clear and most obvious and most insightful. And so it's always helpful to strive for these. So here's one. Do we think that if you study in items, you always make the item, at least in distribution, stronger? In other words, if I have a distribution of new items and a distribution of studied items, does the distribution of studied items have to be larger in some sense, dominate that of new items? So here's EVSD, and the answer here is true. The answer here is yes. This black line, it doesn't mean that every single item is always larger than every other, but in distribution, this black line is a larger distribution than this blue one. This is for new items, that's for old items, and we see that in the cumulatives. The cumulatives, or the CDFs, never cross, right? And so that's a case where if you study items, you always have stronger latent strength in distribution. That means it holds at the 10th percentile, the 20th, the 80th, and so forth, right? And I think that's exactly the right boundary condition. It's not like studying an item makes it less memorable for you. We can agree that studying items make items more memorable as a boundary condition, all right? And so here's another case where you have this kind of dominance. Instead of shifting a normal, I've added an exponential. This is now a normal, that's an X Gaussian. Again, we see this nice dominance in the cumulatives, and this seems like a good boundary condition. Unequal variance signal detection? No. So what happens in unequal variance signal detection is, although most items become stronger in memory, these very weak ones become weaker. They cross in the cumulatives. Studying doesn't have a consistent effect. Some items, when you study them, become stronger, others become weaker. This, to me, seems like a violation that we should be wary of. If this kind of violation happened, and we could bring it under experimental control, that would be one thing. But we should ask the question, do we see these violations? But this model forces you into this violation. Here's a worst case scenario, right? Imagine if study just increased the variance, half the items got weaker, half got stronger. Perfectly fine for you. This is a UVSD model, but as you can see, it's a bit nonsensical. So my boundary condition is stochastic dominance. I want this steady relationship to hold across the entire distribution. I want this concept of unambiguously better. Studying an item makes it unambiguously more memorable. No crossings in the cumulatives. So a robust strength model, if you believe in strength, should not allow violations of stochastic dominance. And it's in this sense that UVSD is not robust. So here's the field structure again for EVSD. So as I increase the studyability or the memorability of a class of items, we go up like this, right? This is the best class of items or the best person, the not so, but these never cross. And it forms like a field. This theory, this model predicts a field, just like a field in physics, like magnetic lines, right? They never cross. This is UVSD. And as you can see in UVSD, they're always crossing each other in all sorts of places. UVSD forces these crossings because UVSD at its core is not stochastically dominant. And so that shows up in the ROC curves as crossings that happen across. It's a messy model that can explain lots of different patterns, and it's unclear what the underlying constraint, either theoretically or in the model world, is. And so in that sense, it's rather not robust. Let's go back to signal detection. So at the core of it, I said latent strength is unidimensional and that responses are governed by distributions relative to criteria. Can we capture this core and what does it mean? One of the things I've discovered is that this core is not enough. It's in fact unfalsifiable. You can take any data and make it signal detection representable. And the easiest way to show this is by construction. So I'm just going to let X be for new items, Y be a distribution for old items. My curve, my ROC curve hits as a function of false alarms. I'm actually going to say, well, X is going to be a uniform between 0 and 1 for new items. And then to calculate Y, I'm going to say the ROC function just follows the cumulatives this way. If I want to know what's the density of Y, all I have to do is differentiate this. And so here's a wacky ROC curve. It goes up in steps. It crosses under. Is this a signal detection model? Well, it turns out we can always represent it. Here are the new items. This blue is for the studied items or the old items. They're both on uniform zero. They're both on the 0-1 interval, and any criteria you push across this goes back and determines this ROC curve. So for any ROC curve, you can always find a one-dimensional latent signal detection representation. In other words, signal detection itself, the core is unfalsifiable. It's a language at best. Okay, so signal detection itself is not robust. Either you buy the normal as part of the process, which to me is arbitrary, or you lose falsifiability. And that's really difficult. UVSD to me is just a hack to fit data. You got to buy into the unequal variance normal, and you have to live within dominance, none of which I really want to do. And so UVSD, EVSD, the signal detection family, to me, is already not a robust way of thinking about cognitive modeling. I think it's injudicious. So what can we do? There may be signal detection models that are robust, at least in my definition of robustness, willing to capture constraints, meeting boundary conditions, giving clear interpretations. What I want to talk about is the concept of unidimensionality itself is too rich. It may seem like one dimension, that's simple, but that dimension itself is too rich. That's really the core of the problem. And so what I'd like to come up with a more restricted version called a scalar difference between curves, or something I'm going to call scalar representability. So to show off scalar representability, these are the new items. And And you can see they follow some wacky shape on the strength. And it could be any arbitrary shape. I'm not too worried about it being normal or exponential, or this is a mixture, but just any wacky shape. The idea behind scalar representability is study only shifts the distribution. So whatever the distribution is for new items, old items, the distribution gets translated. So now we know there's exactly one way that study works. It moves the whole distribution equally, right? And that's the idea. And so that's my question is there a scalar representable form of the data? That way I would know that there has to be just one dimension, and I can characterize how much of an effect their study is by the degree of this translation or this shift. So it turns out EVSD is scalar representable. So these are all the curves, and what I can do to show that is I can transform these, transform the hit rates, transform the false alarm rates by applying a function Q to them, right? And when I apply a function Q to them, I always get a straight line, I always get a slope of 1, and the only thing that differs across these is the intercept, right? And so then that intercept defines the strength. So it's possible to do this with EVSD. This is a gamma signal detection model, all right? And so the black line is new items, the green line is studied items, right? The idea is that we're just changing the scale or rate, and we can always re-represent this as a shift. So these are the ROC curves. They form a nice field. They never cross, right? And they have the nice asymmetry we see in data. And if I find the right function Q, which I know what it is, you can see we can transform all of these into straight lines. Not only are they straight lines, they have the same slope. And since they have the same slope, their intercept defines the strength of each of these lines. All right, so here's another example. This idea of scalar representable might be our way of understanding one process. We have one strength process. If we can linearize the curves, the ROC curves, with some function, and when we linearize them, they all have the same slope, and the only difference is one parameter, the intercept. That, to me, is a single strength model. How about UVSD? Well, here's a bunch of UVSDs. I've drawn them so that the variance gets a little bigger as you add strength, but now you see all of these have different slopes. And there's actually no way of linearizing this set of curves into parallel lines. You need to have different slopes. You can make straight lines, you just can't make them parallel. And so now we know that UVSD is not just a one strength model. We have you can't find a form where it just shifts the curves. That's the point. You have to change both two parameters. And so for me, if we allow this to be a signal detection model of strength, we allow everything to be a signal detection model of strength. We need more constraint. The shift constraint that I think is the right constraint. It's a robust way of thinking about what strength is, and UVSD gets excluded from the family, which I think it should be. All right, so now we're ready to talk about single process versus dual process. I would say we have a recognition memory is single process if we can show scalar representability. That is, we can find transforms that linearize the ROC curves, and we can do so with the same slope, and then we have one dimension of difference, just the intercept, and that's it. Dual process, if we can see these violations and we can bring them under experimental control. We can say, aha, this condition has violations here, that one has violations here, because this one taps one process, that one another one. But obviously, if we can bring these kind of violations of the scalar representability, we know we have a richer set of data. All right, so what I want to do, and I'm thinking I'm at about my half-hour point. I'm hoping I don't have Alexa, what time is it?
It's 8:34 a.m.
I'm not that far off. All right. Let me just make a few take-home points. The first is that theories need to be theories of constraint. We often have theories that are theories of flexibility, like you have multiple processes and things like that, right? Very flexible. Models need to capture theoretical constraint and translate it into statistical constraint on data. Modelers need to know which constraint in their models have psychological content and which do not. Modelers need to be open to constraint in data that is not necessarily of theoretical interest. We also have to be open to find things, right? Like maybe asymmetries in ROC curves. All right, let me finish up with that, and I'm gonna take questions, and we'll go from here. I'm gonna stop sharing my screen so I can see folks. All right.
All right, thank you. That was very interesting.